Hi, Alice. How are you today?
Hi, Zach. I'm doing well. Are you ready? So, today we are going to talk about privacy backdoors.
Excellent, Alice. Indeed, privacy backdoors are a term that's starting to be heard more frequently in the context of large language models. As always, we'll try to understand how this can be done and what the implications are. So, Alice, let's get started. Imagine downloading a ready-made model to fine-tune it for your specific needs. You then share the model with others, but what if
that model was secretly designed
to steal your data? Recent findings reveal a shocking new threat: hidden backdoors in pre-trained models. These sneaky backdoors can allow attackers to reconstruct your sensitive information even if you've taken steps to protect it. Let me introduce you to Mary and John. Mary is an expert machine learning engineer and the attacker in our story. With extensive experience in deep learning and transformers, she decides to implant a privacy backdoor into a model she plans to upload to Hugging Face.
She named it my best PII classifier. PII stands for Personal Identifiable Information.
This transformer-based classifier is designed to determine whether any given text contains PII. Now John, unaware of Mary's intentions, downloads her best PII identifier model to his laptop. John decides to fine-tune the model using his own PII data to improve its performance before putting it to use. When he runs the model, he notices the expected improvement in performance. Satisfied with the results, he decides to share his work with other developers and uploads the fine-tuned model back to Hugging Face. Unbeknownst to him, by doing so, his PII data is now compromised. But even more concerning, even if John decides not to upload the model to Hugging Face and only exposes it via an API that receives text and returns a response, the paper demonstrates how, under certain conditions, PII data can still be compromised. In the next section, we will explain how this backdoor actually works. Here it is.
We will now demonstrate the training process of a multi-layer perceptron, MLP, and how an input injected into a unit can later be reconstructed by an expert. We'll begin by introducing the unit of the neuron. This unit has 3 inputs, which can be represented as a vector with 3 elements. While in practice the number of inputs is typically much larger, for the sake of this example, we'll focus on just 3. A large vector might represent an image, a word, or any other type of information. Each input is associated with weights, which are the well-known parameters of the model. Although we are currently considering just 3 parameters for 3 inputs, in reality, models often contain billions of parameters. Now, let's understand the mechanism that changes the weights of the neuron during training. The goal of the training process is to provide the network with examples of the desired output for each given input. The network then adjusts the weights to reproduce the examples provided by the training set. We will now demonstrate step by step how these weight modifications are made. In our example, the neuron first calculates its output by multiplying each input by its associated weight, summing all 3 elements, and then adding another parameter called the bias, which is associated with the neuron. The input sum plus the bias is then passed through an activation function, in our case ReLU, rectified linear unit, which is complex name for a very simple function that ensures that the output is not negative. Thus, the value of the neuron, represented by the green point, is processed by the activation function and then transferred to the neuron's final output, represented by the red dot. During the training process, this output is compared with the desired output provided in the training set. The difference between the 2 values is calculated, and a reverse process called backpropagation works to close the gap by adjusting the weights. This process is repeated over millions of examples, with the weights being modified so that the system hopefully minimizes the average gap between all the neurons' final outputs and the desired outputs. The orange arrows shown here represent the calculation of both the direction and magnitude of the required modification for each weight, in order to adjust the total output to match the desired output. These orange arrows are called gradients, and they are calculated during the backpropagation process. This exact mechanism operates throughout the entire network, which can scale to millions of units with billions of weights. When the model reaches a point where the gaps can no longer be reduced with the current training set, we say that we have a pre-trained model ready for use. A pre-trained model consists of a collection of weights that were adjusted during the training process. Typically, engineers will take a pre-trained model and use their own data to fine-tune it, following a process similar to the one we've just demonstrated, which means that each weight in the pre-trained model will now be modified by a new weight based on the new data that was used. At this stage, we reach the point where the attacker can steal the data from the fine-tuned model. Let's explore how this happens. As a simple example, let's assume the attacker has access to the model's weights after the first update, and then she calculates the gradients directly. In this simple case, it can be easily shown that by dividing the weight gradients by the bias gradient, the original input used to update the weights can be reconstructed. However, in the scenario we're discussing, the attacker doesn't get to see the gradient updates directly. Instead, they only see the final trained model after many rounds of training. The challenge here is to ensure that the input, which initially triggered the neuron, can still be identified at the end of training, despite being mixed with other data over time. To address this, a backdoor design is proposed where the neuron activates only once and never again. This way, the input that triggered it remains distinct throughout the training, making it easier for the attacker to retrieve it later, even after the model has been trained with other data. This latch mechanism, which allows the neuron's weights to be affected only once, is a more advanced concept. A full description can be found in the references attached to this session. The authors of the paper Privacy Backdoors, Stealing Data with Corrupted Pre-trained Models demonstrate how this can be done without hindering the performance of the entire network.